Welcome to the Explainer. You know, we hear all the time about neural networks having dozens, hundreds, or even thousands of layers. But here is the crazy part. Without one very specific, crucial piece of mathematics inside those layers, all that incredible depth, it's completely useless. Today, we're taking a deep dive into the invisible architecture that actually runs our most powerful AI models, activation functions. Let's get right into it. To really understand the what here, we've got to start with the why. And the best way to do that is to look at this intellectual trap that engineers absolutely had to solve before deep learning could even exist. A neural network is basically just a function approximator, right? It takes an input, applies a mathematical transformation, and spits out an output. But if we only use linear transformations, just multiplying weights and adding biases, we hit a massive, massive brick wall. Think about it. Why would a neural network with 1,000 linear layers be mathematically identical to a network with just one?
Well, let's actually trace the math. If you stack layer upon layer of linear equations, basic algebra takes over. Layer 1 is a weight matrix times your input. Okay, simple enough. Layer 2 applies another weight matrix to that output. But if you substitute those equations into each other, the math just collapses. A weight matrix times a weight matrix is literally just a new weight matrix. So no matter how many linear layers you stack on top of each other, 10, 100, 1,000, the whole network is doing the exact same work as one single linear layer. It's a fundamental algebraic identity. And the problem is, a single linear layer can only draw straight lines.
And that brings us to the famous XOR problem. This beautifully visualizes exactly why straight lines just aren't enough. Imagine a two-dimensional plane, and your goal is to draw a line separating the zeros from the ones. The pairs 0, 0 and 1, 1 output a 0, while 0, 1 and 1, 0 output a 1. Go ahead, try to draw a single straight line to separate those ones from the zeros. You literally can't do it. They are not linearly separable. But the moment we add a nonlinear activation function, we essentially bend and fold that 2D plane until separating them becomes possible. Nonlinearity is the secret sauce that lets a network model if-else logic, or, actually tell the difference between a cat and a dog. Which lands us on the mathematical backbone of deep learning, the Universal Approximation Theorem. This theorem essentially proves that a network with a nonlinear activation can approximate any continuous function. I want you to notice that the word nonlinear there is completely load-bearing. Without that single word, the entire theorem falls apart. By adding that nonlinear function to the end of a linear transformation, the network suddenly gains the theoretical power to represent virtually any complex pattern, curve, or threshold in the universe.
All right, let's move into section 1, S-curves and vanishing gradients.
So, back in the early days, researchers knew they desperately needed nonlinearity, so they used S-curves. But this introduced a major mathematical bottleneck. Look at this number, 0.000001. That is an absolutely terrifying number if you are trying to train a neural network. Here's why. The original default activation function was the sigmoid, which squashes any input into a value between 0 and 1. Now, networks learn through backpropagation, right? Passing gradients backward using the chain rule. Well, the absolute maximum gradient of a sigmoid function is 0.25. If you multiply 0.25 by itself across just 10 layers, it shrinks down to roughly 1/millionth. The gradient basically vanishes. Those early layers get almost zero learning signal, and the network just completely stops learning.
To patch this, engineers made a really deliberate progression. They shifted from sigmoid to tanh, the hyperbolic tangent. Now, tanh has the exact same S-curve shape, and yeah, it still suffers from vanishing gradients for really large inputs, but it brought one absolutely critical fix. See, sigmoid outputs are strictly positive, always between 0 and 1. That means the gradients passed to the next layer are all the exact same sign, which forces the optimizer into these incredibly inefficient zigzagging steps. Tanh, on the other hand, ranges from -1 to 1. It's zero-centered. This means outputs can be positive or negative, which completely eliminates that zigzag problem and allows for much faster, much more stable convergence. So you're probably asking, when do you actually use these today? Are they just historical footnotes? Actually, no. While you wouldn't really use them for modern deep hidden layers, they have very specific architectural homes. Sigmoid is absolutely perfect for the output layer of a binary classification problem, like if you're building a model to ask, is this a cat, yes or no, because it outputs a perfectly clean probability. It's also used heavily for gating mechanisms inside LSTMs. And tanh, it remains the go-to for hidden states in recurrent neural networks and LSTMs, because its bounded, zero-centered nature is perfect for keeping those memory states stable.
Okay, moving on to section 2, ReLU.
the simple breakthrough.
Even with tan, that vanishing gradient problem loomed over deep networks for years, all the way until about 2011. The field desperately needed a breakthrough, and they shattered a decade-long barrier with something that is honestly almost laughably simple. Meet ReLU, the rectified linear unit. The math here is literally just a comparison to zero. If the input is positive, it stays exactly the same. If it's negative, it becomes zero. That's it. That is the entire function. Compared to calculating all those computationally expensive exponentials for sigmoid or tan, this is trivial. It's blindingly fast on modern GPUs.
But the real absolute magic of ReLU is represented by the number 1. For any positive input, the derivative, the gradient, of ReLU is exactly 1. There is no exponential denominator crushing your learning signal. This is huge. It means you can stack 100 layers on top of each other, and as long as those neurons are active, the gradient flows from the very end of the network back to the very beginning at full, uncompromised strength. Zero decay. That simple, beautiful property is what genuinely unlocked deep learning as we know it today.
But as we know, engineering is all about trade-offs. ReLU's greatest strength birthed a new, fatal flaw. Think about it. What happens when a ReLU neuron goes negative? Because ReLU flatlines at exactly 0 for any negative input, its gradient also immediately drops to 0. If a huge weight update or just some bad initialization pushes a neuron's inputs into negative territory, it contributes absolutely no gradient during backpropagation. It gets no updates. It literally permanently switches off. In practice, you can easily end up with 10 to 40% of your network sitting there as dead, wasted parameters. We call this the dying ReLU problem. Let that sink in for a second.
Which brings us nicely to Section 3, fixing the dying neuron problem.
Once engineers diagnosed this specific failure mode, they went right back to the drawing board to design highly specific mathematical patches to keep these neurons alive. And that gives us our 2 main fixes. Leaky ReLU takes the direct approach. Instead of a hard flat 0 for negative inputs, it allows a tiny trickle of a gradient, usually around 0.01. It's just enough of a signal to let dead neurons slowly wake up and rejoin the learning process. ELU, the exponential linear unit, goes a little further. Instead of an abrupt, jagged corner at 0, ELU uses a smooth, exponential curve that saturates at a negative value. And that mathematical smoothness is key. It translates directly to a smoother loss landscape, which gives the optimizer a way easier, faster path to find the minimum without bouncing all over the place.
So grounding this back in your actual code, ReLU is still the absolute, undisputed king for hidden layers in convolutional neural networks and ResNets. It's going to be your default 90% of the time. But leaky ReLU, that is specifically favored in GAN discriminators. Why? Because they process real images full of negative activations, and they desperately need that trickle of gradient to maintain stability. ELU is fantastic when you're building deep networks but you aren't using batch normalization, mostly because its negative saturation naturally pulls the mean activation closer to 0 for you.
Next up, Section 4, Softmax, Competition of Probabilities. Okay, hard pivot here. Everything we've covered up to this point operates on a single number. One input goes in, one output comes out. Softmax plays by entirely different rules. We are officially leaving single numbers behind and entering the world of entire vectors. Softmax doesn't look at neurons individually. It looks at a whole raw vector of scores, what we call logits, and converts them into a probability distribution. Think of it like a competition. Every single class is fiercely competing against each other for a slice of a probability pie that can only ever add up to exactly 100%, or 1.0. To compute the final output for just one element, Softmax literally has to look at and evaluate all the other elements in that vector.
So, you might wonder, why do we use exponentials in the softmax formula instead of just dividing the raw scores like normal fractions? Well, exponentials solve 2 massive problems. First, they handle negative numbers flawlessly, which completely prevents wonky, meaningless negative probabilities. But second, and this is crucial, they aggressively exaggerate differences. A raw score of 5.0 versus 4.9 seems like basically a tie, right? But run them through an exponential function and suddenly it's 148.4 versus 134.3. This winner-takes-more property aggressively forces the network to be highly decisive about its final predictions.
Because it perfectly models that kind of competition, Softmax is almost exclusively used as an output layer function for multi-class classification. If you're categorizing an image into 1,000 different classes, Softmax is your final step. But for those of you tracking the modern LLM space, here's the real kicker. Softmax is literally the mathematical engine sitting inside the attention mechanism of every single transformer model out there, from ChatGPT on down.
It converts those raw compatibility scores between words into the exact probability distribution that tells the AI exactly where to focus its attention.
And finally, Section 5, how to choose your activation.
We've covered the history, the math, and the logic. Now let's turn all of this into a practical cheat sheet for you. Because choosing an activation function isn't just about randomly picking from a drop-down menu in PyTorch. It's about matching the mathematical philosophy of the function to your model's exact specific goal. Need blistering speed and full gradient flow for a massive image classifier? You start with ReLU. Working with time series memory in an LSTM? TAN bounds that state effectively. Trying to balance a GAN discriminator and terrified of dead neurons? Drop in leaky ReLU. Building an attention mechanism from scratch? Softmax is absolutely mandatory to distribute that probability vector.
So, as we wrap up this explainer, I want to leave you with a provocative question. Take a look at your current codebase. Are you making deliberate, calculated choices about how your network bends dimensional space and flows its gradients? Or are you just relying on whatever default your library threw in there? Understanding the why behind these functions gives you the incredible power to debug faster, train deeper, and honestly just build better AI. Thanks so much for joining me on this deep dive into the math that powers modern deep learning. Go experiment with these tools in your own code, and I'll catch you in the next one.